Good morning, everybody. Before going to start my presentation, I would like to extend a special thanks to conference organization, especially Honorable Vice Chancellor Professor Sebu Thomas Sensei, giving the great opportunity to work in this conference. I am Miryala Muralidhar from the Shibara Institute of Technology. It is my highest honor and my great pleasure to deliver today's keynote talk regarding the development of superconducting supermagnets for day-to-life applications. So, sorry, here is my presentation contents. First, I will give a brief introduction of SIT and also superconductivity. Second, I will show the high TC superconducting material development and application of bulk LRE123 material. In this case, I will concentrate on low cost and high performance LRE123 material and some of the applications. Then I will present the development of DC superconducting cable for the railway applications. Finally, I will conclude with the summary of my talk. So our university was founded in 1927 by Professor Shiro Hashimoto with a motive of nurturing particle engineers who learn from the society and contribute to the society. Our university is in downtown Tokyo. It is very close to the Olympic 2020. However, due to the pandemic, it was cancelled. So SIT has 3 campuses, 2 in Tokyo area, that is very close to the Tokyo station, like a 10 minutes ride by the Minamoto line. That is one is in the Toesu and another is like the Shibara campus. And one is Saitama, about 30 kilometers to the north of the capital. This is very close to the Higashi-Omiya station. As for the globalization process, the mission of SIT is fostering scientists and engineers who learn from the world and contribute the global sustainability. Our university is almost all like a curriculum is on the basis of SDG goals. And also SIT is devoted to excellence in teaching and research. As a result, 95.6% of students will confirm the jobs during the starting of 4th grade, that is the specialty. Our strategic goal is top 10 technical universities in Asia towards the Centennial SIT action, that is the 100 years of SIT, that is 2027. We choose 3 ranking systems like QS and Times Higher Education, Thomas, working very hard to reach this goal. I would like to share one thing. SIT is one of the country's top global universities, selected by the government of Japan to be role model for globalization of the Japanese educational institutions. Times Higher Education, Chonchi. Japanese university ranking is 35 out of 780 universities. And also in framework of the globalization process, SIT is send our students to the abroad, especially like short-term and long-term programs. Is the one of the goal. You can see like starting our program, like 118 students inbound and 119 is outbound. But today is more than 1,075 students for inbound, and outbound is like more than 1,000. But this is like a really lower data. But our main goal is end of the top global university project, our mission to send all our students to the abroad. To make this such internal exchange programs more attractive, we are organizing the part of global project-based learning. Is like active learning. Problem-based learning means that is a project or practice-based. Example, you can drive the car even if you learn the structure and function of the textbooks. We cannot. Because what I hear, I forget. What I see, I remember. What I do, I understand the principle of the active learning. Most of the courses, most of the programs in our university is the active learning. And also, this is the very good opportunity to study abroad, like foreign students in SIT. SIT have several English programs. One is the global program, just we recently started in 2017. This is the mainly for the Japanese students abroad for the one semester. They will go and abroad, and this 6 months, one semester they can supposed to complete. And second one is global program, the master is like this is also launched the same year, but international and Japanese students can be participate, but Japanese students must be abroad experience at least 3 months. On the other hand, international students supposed to be like Japanese companies, they must do like 3 to 6 months. And one more important, we are also starting like a global innovative engineering program. That is like based on undergraduate program, 100% in English. It will be start in 2020 for the September. Students will be join laboratory from the first year onwards. Before going to start, I will show some more like we will do like advanced project based learning, that is called APBL. In this, with SIT efforts to introduce active learning, is a short-term international educational program. Typically, for the 1 week to 12 days, where students from the member universities, from the multicultural teams collaborate in the finding solutions of the research-based problems. This is the structure. You can see the left-hand side. Students work in APBL projects, mainly like APBL means advanced. That's why we are doing the research-based projects, involve the SIT students. They analyze their data, and eventually they must publish the research paper. This is another example. This is the APBL program just we conducted before last year. Here, like I invited like IIT Madras, 10 students and 2 professors. Then IIT Delhi, 6 students and 1 professor. UPM, University of Uttar Malaysia, Professor Chen is here. I'm very thankful for the Chen sensei. Like 5 students and 1 professor, and KMUTT 4 students and 1 professor. Eventually, like 30 students plus including 5 professors from the abroad, and also our SIT students and staff involved in this project. This is the main idea is collaborative research leading to a strong and numerous research publications. Eventually, we published more than I think 8 papers up to date in this after this from this our output of this program. And one more thing I would like to all these programs will be main idea to increase our ranking. Of course, it will be also useful for our partners. Second one is the PH Innovative program. This program has been very successful and effective in increasing the number of international peer-reviewed papers. Normally, this program was started 3 years back. We will select the students from the elite universities. They will be carry their research in the more than 3 months at our SIT laboratories, publish results in the international journals. I can show like this is like one batch of students. Like this is the financial year 2017. Like most of the students from the IIT Madras, all are PhD students. They published more than 10 papers within 1 year financial year. Like the 2016 students, they published 2017, like 17 students and 18, but it will be take publication process. But it's like such a programs. It's not only this one. We have like a Sakura Science program to invite the students, and also internship program to for the bachelor and master, like short term to long term. Anyone interested, welcome to SIT. That is my first part of the talk. Then I will be give some introduction. Like now the global energy and environment, like global issues are raw fuel reservoirs are limited, energy usage is increasing, and pressure of standard living. Everybody want to enjoy the life, but apart from that, global warming another problem. For example, you can see like here the world reservoirs like coal, especially. You can see like data normalized to the peak value. The country with the world's largest proven coal reservoirs as of the 2019 was the United States. That is marked with the red. Most of the coal is US, Russia, China, India, Australia is also some of the peaks are there. Then also, if you look the gas reservoirs, Russia top the list, holding about a quarter of the world's total gas reservoirs, followed by Iran and Qatar and Middle East. And next is the oil reservoirs. Normally, people are using for the long time. Saudi Arabia is the world's largest producer and exporter of the oil, and has one water of the world's known oil reservoirs, more than 260 barrels. But the question is, how long will be the support will be lost? But when you ask for the international advisory, oil and natural gas will be 50 years, they are predicting, and coal is 300 years, but it's just only like most of the thing in the USA. Oil shales and or strands also same thing. Nuclear fission and nuclear type energy is the people are worried about the after the Chernobyl and this Fukushima incidents, that only major is the renewable energy sources, of course. But another thing is like global warming. Global warming, like carbon dioxide is an important heat trapping gas which is released through the human activities. That's why even though you can see the left hand chain like CO2 levels was like predict 1950 onwards steadily increasing. Latest measurement is the right side, like September 16, 2019, 412.08 ppm was recorded. As for the EPA, Environmental Protection Agency, they already declared like Earth average temperature is rising like 0.8 degrees centigrade over the past century. Then it will be raise another 2 to 6.4 degrees centigrade over the next 100 years. This is the one of the major issue, major problem in the world-wise. When you look back to the thing, like world primary energy demands is like 40% between 2007 to 2030, and again like 2050 is the predicting like 80%. But however, like coal is one of the remaining. If you see that this figure, still people are depending on coal and oil. This non-renewable energy sources. It is very difficulty for the our for further to reduce the like CO2 emission to control the global warming. So I can say like to clean environmental becoming the priority in this stage by adapting the environmental friendly technologies, and material processing is very, very important. For that, to increase the efficiency and control the global warming, we need to employ like new technologies. That I can say the superconductivity is the one of the best way. So I want to introduce superconductivity. Like my PhD is in superconductivity. My educational background mainly focus on superconducting and its phenomena, which create the potential and revolutionary our current generation in the respective fields, like especially like medicine and transport and energy savings. You can see the left hand side figure, the levitation of the magnet above the neodymium europium gadolinium material is the bottom of the sample. That this is the normally this the levitation of the magnet and superconductor, we can say like Messner effect. But if you see the AFM measurements, like we will be create like nano pinning centers during the processing, it will be, we can say like a flux spinning effect. As a resultant, now one can levitate very heavy object. So the new phenomena were attracted many outstanding people. Levitation of sumo vessel with a high temperature superconductor. You can see the right side figure. And also like superconductor have the ability to conduct electricity without the loss of energy. When current flows in an ordinary conductor, for example copper wire, or some energy is lost. So here is like you can see the left hand side figure, the top one. Electricity wire has a resistance that disturb the flow of electricity as a starting point and destination. Electricity always 7 to 8% losses. In the bottom figure, you can see like the starting point in the superconductors. You can see ending point like 100% of the electricity will be arrived. That's why we will say like the superconductor means electricity flows super smoothly. This phenomena, like in 1911, superconductivity was first observed in mercury by Dutch physicist H.K. Honus of the Leiden University. When he cooled to the temperature of liquid helium 4 degree Kelvin, that is like minus 269 degrees centigrade, its resistance suddenly drops. Then this phenomena, you can see the first mercury main plate here, the right hand side, resistivity versus temperature. As a resultant, like HK won a award in 1913 Nobel Prize of Discovery of Superconductivity. So the next is the great phenomena is superconducting, this picture below is the levitation of the magnet above the cooling the superconductor. This is the Meissner effect. When a material makes the transition from the normal superconducting state, it actually excludes the magnetic flux. That's why it is levitating. Here, you can see like two things like HC, like a critical magnetic field. Below is the normal conductor, above the perfect diamagnet. That's why that is called the Meissner state. But in this material, like normally, if you apply more than 1000 Gauss of electromagnetic normally superconductivity will destroy. That's why they could not make the superconducting magnet after discovery of superconductivity. Such materials we can call like type 1 superconductors. But later, like so many materials were discovered, hundreds of materials like metals, semiconductors, insulators, almost all like several materials. But in 1955 to 60 range, they discovered the type 2 superconductor. In this case, like type 2 super has a two critical magnetic field, that is SC1 and SC2. Below SC1, type 1 behaves like the type 1, type 2 behaves like type 1, and above SC2 becomes the normal. Here, I want to say like this is a mixed state. The superconductivity and like magnetic flux can be penetrate. Such a mixed state is the more viable and is very, one can make like superconducting magnets due to the mixed state. That is like almost like recently discovered YBCO and also MgB2 also is the type 2 materials. So the discovery of YBCO superconductor in 1987 was a significant turning point for the superconductivity. Most of the countries worldwide is working for the superconducting material after this discovery. The new material shows the superconducting transition temperature above liquid nitrogen temperature. That is the breaking point, like 77 Kelvin. That's around superconducting transition temperature is the 90 K. Liquid nitrogen is the very cheap, like mineral water, and difficulty to evaporate as compared to liquid helium. And also like one can generate very easily from the air. So many benefits. That's why worldwide people are working and changing. They want to change the everything. But a lot of people are working and there are a lot of progress, one can say. Here we are concentrating like YBCO, yttrium barium copper oxide, NDBCO, neodymium barium, gadolinium, and also like several materials NEAG. So you can see like development of why we want to make a multi-structure ITC superconductors, because like HTSA materials very strong, permanent magnet 100 times more powerful than the ferromagnets. That is main idea to use these magnets for several industrial applications. This is the video you can see like permanent magnets, so we cannot generate more than 1.5 Tesla. This is even the special case, but in the superconducting magnets is entirely different. We already in SIRLC stake while working, we are demonstrated like 17 Tesla at 29 Kelvin, 3 Tesla at 77 Kelvin in the gadolinium 123 system, and also interesting 1.5 Tesla at 90 Kelvin. That is a liquid oxygen temperature, not liquid nitrogen temperature. That all this is the depends upon the JC and critical current, the sample size. So in this process, we started like 2 mm to we reached the 140 mm bulk superconducting magnet. And also we work to improve the JC values. You can see this is the very easy material can be processed starting from the oxides, then we can mixing into the normal process, and also like sintering, calcination. Then finally we can make the pellet, then insert to the such a furnace. Then is the finally we can material can be heated to the more than 1000 degrees centigrade and cool to the below 1000 degrees centigrade, 1 degree centigrade per hour. Why we have to cool? That is the we already demonstrated. Like this is like due to the pyritatic reaction below 1000 degrees centigrade, 211 plus liquid form to the 123. Then we can get the very high structured material. This is the one of the everybody is working is a stake in different materials. I concentrated like to improve the performance because everybody say single grain material like yttrium, neodymium, samarium, but after a certain you can see like here like YBCO almost all like will be JC will be goes down, but in the case of NDBCO a little bit improvement in the 2 Tesla. But when you use that mixed system like ternary superconductor compound, there is the 3 light rare elements elementary cell, new class of high TC superconductor, that is like neodymium, europium, gadolinium. Of course, we prepared several samples, but NEG given the very good values. In this case, you can find like very high critical current densities in the 2 Tesla. When you add the samples, the 40 mole percent of 211 as a resultant, the world highest supercurrent density in the high fields are more than 3.5 Tesla. This result was several patents, United States and Europe, as well as like the press release in Japan. Of course, then the further improvement of heterogeneity field was observed, especially in the europium rich direction. You can see like when you make the europium 0.38, gadolinium 0.28, this is the data what I showed the 5 Tesla. It become to the, this is also 77 Kelvin magnetization versus magnetic field. You can see like 12.5 Tesla at la 3 mole percent of NEG, europium rich NEG to one sample. But in the case of like if you improve the 5 mole percent, it is more like more than 15 Tesla. This is the one of the champion data up to date. This the when you measure the critical current density, like critical current density at 70 kiloamps per centimeter square at the peak value, that is like around 4.5 Tesla. And irreversibility field measured by the VSM, we found like 50 Tesla at 77 Kelvin. Then we concluded why such a high critical current density in this material. When we observed correlated pinning disorder, means nanoscale lamellar structure, what we saw in the TEM in the right side picture. This is the variation of chemical ratio, NEG by BA ratio, and hence the flux spinning as a resultant tremendous improvement in the irreversibility field at a high magnetic field. So you can see like nanostructures, it is close to around 4 nanometers. Like it is close to the coherence length. As a resultant, it was improved. This results also like the world highest irreversibility field so far reported is a 15 Tesla. Then this is also again in the press release and TV channels in Japan. And also further, our main is to improve the critical current density. Then we again concentrated like so many things like niobium nanoparticles, molybdenum nanoparticles. As a resultant, we found the new type of 211 particles. As a resultant, the critical current density was improved the 90 Kelvin. That is the liquid oxygen. As a resultant, one can levitate the material like liquid oxygen temperature, not like liquid nitrogen. You can see the figure, that is the blue color like liquid oxygen. This is the peer review. This is also again like, 2 patents as well as like results in the press. So like that, we improved the JC tremendously. But the thing is, when you buying the samples, of course, in Japan as well as German and also like Czechoslovakia, now the selling $300 for the 1 centimeter of the bulk sample. To reduce the price, we used the batch processing. In this case, like of course, production quality and number of grains and equipment cost and loss of fraction is the very important. To control this thing, we developed the huge batch type furnace. With well, we are working in the Railway Technical Research Institute. Large utility volume we selected, and we maintained the uniform temperature throughout the furnace. That case, we use the 6 type of stranded element heating coils, and the temperature gradient to maintain like top and bottom surfaces around 2 degrees centigrade. Here, to successful such a story, a novel thin film of neodymium 123 seed grown on MgV crystals was used, and we adapted like a 2-step heat processing. Then finally, we found like very good like a first report on like LRE 123 batch production. This was highlighted in the superconducting science and technology. Such a result, you can see like batch 1, batch 2, batch 3, even though 24 mm to 45 mm batch production samples were done. But however, to see the performance of the GD123 material, we did the trapped field measurements at 77 Kelvin and also high temperatures like liquid argon 87.3 Kelvin. This give the, like, you can see the trapping, no, more than 1.4 Tesla at 77 Kelvin, around 45 samples. And also the same sample is trapping like even the liquid argon temperature. So it will clearly indicate that one can use such a material for the real applications like the superconducting supermagnets. And also this levitation of women we did like 1996 in Aztec. But in when taking advantage of the batch process gadolinium 123 sample, just 45 samples is enough to levitate the very heavy objectives, but shown in the right side figure. And application where we can use, of course, medical and health is very, very important. So this already shown the magnetic field distribution is the like steep field gradient, very sharp. This is the bulk superconductor. When you see the solenoid coils is the rather flat and not uniform. So strong and steep field gradient generated by HTC materials will be control the drug and distribution of the particle of like in this material. Then we, our ISTEC, our sensors propose like a human's body is so complicated that control the drug delivery will be extremely difficult. But instead of delivery, we will be extract strong magnetic fields on the desired part. Then the medicine with the magnetic particles, like small Fe particles, with the magnetic field, the medicine will be stay the desired part. But this will be minimize the drug effect. But is normally, no, this is the left hand side picture, drug delivery system. This developed in the NIDO project in the superconducting research laboratory. This is the basic idea, like magnetic force of the magnetic seeding drug with the ferromagnetic fine particles is the induced by the superconducting bulk magnet. The magnet is placed outside of the body, then one can control. This is the idea, but this was we cannot use directly for the human beings. Though we made like pig and also rat. This is successful for this experiment. I think in the future it will be more attractive application. And also like novel medicine treatment without surgery. Also, this is like we propose the new medical treatment regeneration situation of mankind. Hope it will be work in the future. Here also same thing. Stem cells with the magnetic particles will be injected by the injected by the syringe and make the outside the bulk superconducting magnet around 5 Tesla. But in this case, always we need the bulk superconductor that generate the high magnetic field more than 5 Tesla and small area like 2 centimeters. In that, our PhD students and master students working to develop the more strong magnets to work at around 77 Kelvin. And also like magnetic separation and bulk superconducting magnets is the very powerful. So that already experimentally proven over 90% removal particles, high speed treatment, and 1/10 flat area, like because due to the compact. This is the main idea is like polluted water always containing the ferromagnetic powder is very cheap. Then one can use the bulk superconducting magnet more than 5 Tesla. As a resultant, one can get the clean water. You can see the result already laboratory result, like removal rate is 95%. It will be very useful for the like especially like lakes and ponds to clean. Even though Saudi Arabia and India, so many countries having the water cleaning is the one of the major issue like ponds and things. And also we developed the using the like a strong superconducting magnets. Like one can make like the annular type ring magnet. Here is especially like one can arrange the samples like different shapes like 1, 2, 3, 4 like that. Especially we found the increasing the number of ring magnets, the magnetic field strength was improved at the center of the magnet, which shows that these bulk ring magnets one can be use the superconducting permanent magnets. You can see the left hand figure. If you use like 4 magnets, 2.0 Tesla at center of the magnet itself. But in the case of 10 ring magnets, it will be more than 2.6 Tesla. Using these advantages, we developed the like a compact, lightweight, powerful superconducting portable superconducting magnet. You can see here this actually this is the very, very portable and very small, very compact. One can generate 2.6 Tesla magnetic field. And then we try to see like superconducting magnets, magnetic performance. Like this is a 10 Tesla like bismuth 53 magnet. And like this is the another is this is the normal we constructed magnet. Here is the magnet with the 10 Tesla superconducting magnet. Results are very nice. This one can use this like especially like NMR applications in the future, and also like drug recovery systems. Of course, I want to concentrate last the transport. Like transport, everybody knows maglev trains may be the most environmental friendly transportation. You can see the CO2 discharge from airplane to maglev direction, but this is the worldwide problem. We have to reduce the carbon dioxide emission, means we have to go like maglev type is the more important. And also maglev trains may be the fastest and safest. You can see like 600 kilometers per hour is the maglev, and also maglev evacuated to more than 1200 kilometers per hour. People are working. Oh, this is like master plan of the maglev is started in JR in 1960s. JR first experimental train is we are shown the left hand side. This is the ML100. Maximum speed is 60 kilometers. Weight is 3.5. And 4 years then Japan National Railways was working after this. They did like maglev like 1970s, like 7 kilometer track. Then eventually they moved to the Yamanashi test center, that is like more than 40 kilometers track. Then they showed 600 kilometers per hour in 2013. Eventually these trials are so successful, now they are planning to use like reality like Tokyo and Nagoya in 2027. That is like 360 kilometers within 40 minutes. For this we will start the public. Here they use the superconducting super magnets, and also, but it's all using like at the moment neodymium coils. But in the future, if you use the YBCO or NEGs type superconducting magnets, it will be very cheap. We already shown like even though taking advantage of bulk material, we constructed the vehicle. You can see, I want to skip this one, like magnetic track, then cooling the material, and this is like 3 to 6 meters railway track. The one can use like bulk material to generate such a thing, and also such a 77 Kelvin vehicles were already demonstrated, like China, Russia, and Germany. And also maglev tube, like HTC maglev evacuated tube, also like working in China. Now they are almost all like already shown 300 kilometers per hour. They have predicted, but they already shown like 160 kilometers per hour in the before last year. And final part, I would like to say like some of the result what we did in the power transmission is the one of the major issue in what I presented in the introduction session. Because no, even though railways, they have several tasks, they have to give the environmental friendly railways, and also reliability, economy and econominess, everything. But as for the Kyoto Protocol, Japanese government thought like 1990 to 2060, 6% reduction of the CO2 emission, and 1990 to 2020, 25% reduction. However, what they see like 1990 to 2019, 4% was increased, not decreased. Then I think like further like superconducting technologies were very important. Then we proposed the DC superconducting cable. When we are working there, that's the project was started. Like where one can use this such a high TC superconducting DC cables is the one of the question mark. But when you look the Japan Railways, this is the red mark. It's the not like Okinawa to Hokkaido, more than 20,000 kilometers of DC cables, especially like 36% is the conventional lines, and 71% is the private lines. Okay, what will be the benefit if you use like DC cables instead of the normal cable? Now we have like, you can see like a red one, HTSC DC cable, the normal copper cable. But if you, this is the one of the major is the spacing between the transformer substations is like 25 kilometers. But here, if you use the copper cables, normally they are using like 2 kilometers because of the voltage decay. And also like CO2 emission one can be reduced, and the compactness will be goes like such a metropolitan cities. This is one of the major advantage. So that we started this project benefit of the HTAC cable, like major is the load leveling, means we can maintain the voltage, and the energy saving around 7%. CO2 emission reduction is the 100%. Here this the picture. We can see like a positive terminal of the reactor connected to the quaternary wire, and a negative terminal is connected to the rail. Both quaternary wire rail bring to the power to the train. As a result, and will be moved to the. But normal case here is the like copper cables. If you use the superconducting cable, one can be delete such a substations and the reduction of this energy losses. So we started like 2-meter cable. First, we don't know because they need the 1.5 kV. Then this 2-meter cable, like bismuth 2223, like the bismuth 2223, you can see like this is the basic schematic cross section. What we used here is the 2-meter cable length. Then we like local made cryostat was developed to cool this 2-meter cable, and it tested the current characteristics. You can see like conductor layer and shielding layer. Conductor layer normally we will use the positive terminal and shielding layer the negative terminal. So that these two layers, superconducting wires, you can see like 1.7 kV to 3.2 kV. These results clearly indicate that like one can use DC cables for the system. But one more thing, an application point of view, it is important to test the effect of liquid magnetic field during the current flow, since especially in the Japan, railways tracks are very close to the residential areas. That's why just we try to see the, of course, if liquid magnetic means if it is very close, almost all TVs cannot be clear, and also like hospitals, like electrocardiograms will be damaged. Then we try to see the liquid magnetic field is perfect, is clear, is almost all both conductor layer and shielding negligible liquid magnetic field found. When we set the current both opposite directions, no? They almost all the liquid magnetic field is 0. Then we say, oh, it is very clear, it is perfect. Then we ordered like a 5-meter cable. In this case, what we first we use the copper cable, no? This copper former is very heavy. Then second stage the aluminum. Then also they made the hole to pass the liquid nitrogen, and also to control the like fault currents. Along with the superconducting layer, we used the copper protection layer, both like positive and negative. Then we tested the IV curve from the bismuth 223 5-meter cable dipping in the liquid nitrogen temperature. You can see like here is the 5-meter cable, and like 5 kilometer cable was dipped into the just like LN2 bath. Then we found like more than 1.3 around like 1.1 kV. This is very close to what we expected. Then next design we improved the superconducting tapes to further improve the thing. Then this is the final 30 meters and 3-meter long HTAC cable. Here you can see the liquid nitrogen pass from the here. This is the copper protection layer and HTAC conducting layer. Then insulator. Then HTAC shielding layer and HTAC protection layer. So liquid goes from the center, but then it comes to the back of the protection layer. So this cryostat, everything was designed. Then we made like a 30 meters and 3-meter long cable, and here is the 30-meter long bismuth 223 HTC cable is like installed at Railway Technical Research Institute. Is the this cable is length is around 31 meters. And also to see the performance, like we buried the 15-meter spot. You can see like buried means like if you go into the ground, and also like horizontal bending 5 meters and vertical bending 5 meters. Then we constructed, this is the construction area. We connected to the one end to another end. Then this is the 30 meters cable. Then we did the performance test. And also then we also just moved to the 30 meters long bismuth 223 cable. This is also like you can see like the same thing with buried and also bedded, because due to the real application we need all these type of technologies. Then eventually 3-meter bismuth 223 cable successfully connected to the train and succeeded train running test. This is the one of the more like next generation DC cables, like a new project. Then this like now the one can use like such a technology using the DC superconducting cable. Now the Miyazaki test area, they are planned to 3 to 4 kilometer track DC cable project is under the way with utilizing the solar energy, because DC is the direct current. One can connect if there is no way to AC to DC conversion, one can use directly. This is the next generation railway system, like superconducting technology and renewable energy sources. You can see the natural energy gas, like load leveling, energy saving, CO2 emission can be reduced by using the solar and wind energies. Of course, this developed energy can store the HVAC power storage devices like the superconducting power. Then we can connect it to the such a energy to the railways. So I think HVAC cables not only here but also in the future, is especially such our countries like especially in the winter, one can depend upon the like Sahara desert or something. They such a produce the electricity can be transport only like this was 2 to 3 cables. Now the Sumitomo industry is producing the kilometers of wire for the commercially. This is the summary of my talk. Anyhow, I'm already 1 minute, 2 minutes. Yes. So this finally, I would like to thank to everyone. Here is our team members, like professors and PhD students and master and doctoral students. Thank you very much for listening my talk.